Right, so sorry for a little bit inconvenience on the technical stuff. Seems like there, I, I don't know. I thought that I put it as a recurring meetings, but somehow it turns out it was set as the one-time meetings. So that's why many of you cannot log in. So maybe I should remove the old link so that you won't accidentally log into that. Not sure if I have put it in the link down there. No. Okay. I'll probably have to fix the syllabus because I think there's the link there. But I'll do that later on. Okay. Yeah. Let me prepare this. I will have to use the iPad as well for writing the note. You guys, let me open it. Deep learning. CPE. No. Yeah, CPE. Deep learning 1/2020. Okay, and then I have to join Zoom. Join the meeting. Start. Continue. Cancel. Turn off. Have to turn this off as well. Okay. Right. And I have to put the. Oh, how come? I have already turned off the waiting room. Everyone should be admitted automatically. Okay. Okay. Thank you everyone. Sorry, it's a little bit messy today. Switch from one meeting to another meeting, and let's start. Yeah. Let's start. We will in our class today. We will cover the topics of gradient-based optimization, which is the parameter estimation technique that has been used in deep learning. So learning it today will allow you to understand why you have when you choose certain technique for learning like Adam, Nedam. Why do you want to choose them? What are the underlying parameters associating with each of the optimization technique, and how does it work in terms of the gradient optimization? Understanding gradient optimization will allow us to know why logistic regression behave that way, and you have a chance to do the assignment. Right, today we will have our first assignment, which is a programming assignment that you have to write code from scratch. You have to write the gradient optimization on your own using a basic logistic regression with a little bit modification to have like fun applications that you can work on, right? So that's what we are going to learn today, and I think without wait, let's start. And you can ask any questions during the lectures. I don't have to hesitate on if you have any questions in mind. Just put it in the chat. Okay, so the topic is gradient-based optimization. So we are going to take a look on how it works. So basically, what we will look at today is the technique called gradient descent and how it works in mathematical sense and in computational sense. In the there is a field in research, in the fields in operational research called optimization. Optimization is a task to identify parameters, to identify the solution that you want to estimate. And that solution has to minimize or maximize the objective functions. Okay? Objective function can be any types of functions that is expressed in terms of the thing that you want. It can be things about reward, about cost, about error, or about other things, right? So by expressing this as function, you have an option to optimize them, which means that you can find the best input that will give you the best output from the optimization function, from the objective function, right? So in our case here, we want an optimization to find x, to find the best parameters, the best vector x, or the parameters that you want to optimize, by minimize this function fx. In machine learning, this fx function can be the loss function, the error functions, right? We want to minimize them so that our model fit with the data, right? And similar types of problems arise in many fields, right? One of my research on speech modeling is to find, also work as an optimization problem like this, but instead of optimizing the machine learning model, my work is like I propose that the model or the explanation of the process should be in a certain mathematical formula, and in that I have defined the mathematical formula, and in that formula it contains a number of parameters that you need to estimate from the data itself. So what I did back then was to create an optimization program that take input and test it out, and then iteratively optimize the parameters of the model, so that once I got the parameters, I can use those parameters to explain the process. Thus create more understandings of the process by doing that step. So optimization allows you to study, not just in machine learning, it allows you to study, perform numerical analysis in many other fields. Right? In my case, it's speech science and engineering, but you can also do that with finance, with physics, and others. So in optimization, you need to define this. You need to define the objective function. The objective function. The objective function is the function that you want to minimize or maximize. It can be defined as a cost function. Right? This can be a function about the cost of usage. It can be the function if we talk about investment and you want to, or if we talk about a task like supply chain, you may want to optimize the cost of supply chain, and you can create an objective function as a cost function. It can be an error function, which define the difference between a predicted value and the model, the predicted value and the actual values. It can be defined as the loss function, which actually is similar to an error function here, but more towards categorical loss, that when you select, when you predict as one class, how good is that, right? So you can define it as loss function, right? And we will take a look at that today for logistic regression, right? So let's talk about, before we begin with how to find the best value for the objective function, let's define this value, the gradient. The gradient is the derivative of function. Right? If we have a function fx, whatever that function is, we can perform derivative by computing or deriving the f prime x. This f prime x is denoted as dy by dx, right? Depending on, so what does it mean by dy by dx? This dy by dx meant that you are calculating the change of y with respect to the change of x. So if x change, if the value itself is positive, it means that if you increase x, y will also increase. If the value is negative, it indicates that if you increase x, y would be decreased, right? On the other hand, if the values of, or the formula of dy by dx is depending on an expression, is depending on another variables, that means the change of x would depend on the value of another variables. Right? So when you interpret interpret the derivative, think about it as gradient, or what happened when you increase the value of that of the parameters. What will happen to the function? Okay. So the derivative here in the geometric sense, it gives you the slope of fx at point x. That means if I write, okay, I should be annotated. Okay, so if I write a function like this one and say calculating the f prime x at this point, what I'm getting here is the slope, right, the tangent, the slope at point x. So this will be the tangent at this point x. Okay. So this is f prime x. In other words, right, we could specify this small change or this gradient as corresponding to something like this one, because we are the prom here indicate what would happen if you make a very small change, right? This would be the rate of change of the values if the difference is say 1. So that means if we make a very small change like this one, epsilon, right? X plus epsilon means that we have something like this function, and we have a certain value x here, and say we have this very small infinitesimal increase x plus epsilon, then the value of the next one, the value of this point, would comes from the previous point plus the difference between them, and this difference between them comes from the slope that touch through this and then multiply with the step size, the epsilon here. So if we talk about a very small change, this would be valid. That is the infinitesimal change in the x input would can be calculated, and the y of this infinitesimal would comes from or can be approximated as the value of fx itself and the difference time the prom, the change, right? So here it indicated like this. We have this value of 1 over x squared, and the difference, the diff of this is x. That means if at the point of 0 here, we are at the global minimum of x equals 0, and the diff of x, the derivative of x would be 0 at this point. This value would be x, and at the positive side, the derivative would be plus, and the negative side, the derivative would be minus, which indicate what would happen when you change the value of x. You can see that at this side, changing the value of x resulting in downward step, while on this side, changing the value of x incur the increased incremental step, right, the upward step. So gradient will tell you the direction of change, basically that. So and what would happen when gradient is 0? So you may think that, okay, so just like in the least square, right, method, in the least square, when you that I have reviewed when you do the pseudo inverse, if you can define the systems of equation and take the derivative of the function or the system of the equation and equate them to 0, you can find the solution of the system, right? Because the derivative of the function equal to 0 would indicate the turning point, the critical point of the function. However, the first derivative of the function would indicate that there's no change and no gradient at this point, but it doesn't tell you whether this is minimum point, maximum point, or whether it is a saddle point. To make matter worse, if your data are complicated and the model are also complicated, and then you want to fit them together, there might be a point that is minimum but not the actual global minimum, right? And we call that the local minimum, the local optimum. What does that mean? It means that you may have a complicated function, and this point also have the f prime x equals 0, right? The same for this point as well. But well, without any good method for estimating the parameters, if we just find the lowest point and equate them to 0, there is no guarantee whether we will find the actual solution. Right. Now, suppose we have multiple input. We just talk about the gradient of one input, right, x. And when we change x, it will tell us, when we change x, the result would be observed in fx, and the diff of fx by dx would tell us the rate of change or the gradient of that function. But when we have, in deep learning, in many times in deep learning, we have multiple input, right? That means we cannot just take derivative of one input. We have multiple parameters to estimate. We cannot estimate or take derivative of just one parameter. So we need to find the partial derivative because there are multiple parameters. The partial derivative here, if we interpret it as in terms of the physical interpretation, this would mean this is the measurement of what happened if how f would change if we think about just one variable. If x increase, what would happen? So you can think of this as when we fixing the like if we talk about, well, better way would be viewing things as 3 dimension. Something like this one. And if we take a derivative of this by x, let's say this is x, this is y, this is z, supposedly. If we take a derivative of it by x, it means that we are treating z and y as constant, and we view everything as the x-axis. So the result would be something like the perspective of these three. Come on, oh, it's over here. Right, of this 3-dimension graph, so that it's like we are viewing the change only in this direction and disregard the other direction. Right, so this is the partial derivative. Okay. So the gradient of the partial derivative here and also in the book is denoted as this symbol. This is the gradient of partial derivative of x of function fx. Okay. And when we write it like this one, the element I, if we take the partial derivative x of x, and x is a vector, then it means that we also take derivative of the element of xi here. So when we have multiple input, one of the critical thing would be we need to find gradient, the point that is a gradient equals 0 of each input. How does it work, right? Because there are multiple input often associated in deep learning. For example, you may have the node looks like this. Now we have like 4 input, and each input also associate with the earlier one until the end, like this one. That means there are multiple inputs, and at each layers there are actually multiple links between input and the node in different layers. So when we consider this and we want to update the values inside this, we need to find a way that we will use the gradient here in order to update the parameters, in order to make the parameters better. Okay, that's the idea. Because we cannot just find the parameters at one go, like having input and output, and then ta-da, we get the parameter. It doesn't work like that. Right? The idea of finding the best parameter is to iteratively update the parameters. Like we have data, input and output, and then we use let's say we try it once, and then update everything, try twice, update everything, just keep doing that, right, until the network reach certain point that is the best point. Okay, and in order to do so, we need to find the update, the gradient, but the gradient of what, you will see that later on. All right, let's take a look at this gradient first, and how gradient relate to the direction of function, because later on in this lecture we will change this function into error function, and then we are now talking about how changing parameters, how changing the x would affect the error function. Let me turn this off, it's a little bit annoying. Okay, and this as well. I'll turn everything off already. Okay, so let's take a look at the direction of gradient. How do we find the direction of gradient of a certain function? The direction of gradient comes from the derivative, right? Directional derivative in direction u, right? Let's say u is a unit vector that is a slope of f in direction u. So it means that we are trying to find the partial derivative of the function with respect to certain parameters, and the result is still a vector, right? It's still the vector of the function. Okay. So in other words, to say is a simpler term, right? So what we call the direction of gradient or directional derivative, right? It's the derivative of the function. Like we have the function that looks like this. This is the function fx plus alpha u, right? U is the unit vector, and alpha is a certain value that we want to estimate, and we want to evaluate that when alpha approach 0, right? A very small value, a small change at this. So if we using the chain rule to estimate what would happen to the gradient, we would have something like fx plus alpha u here, and we take the derivative of alpha by the whole thing here, and evaluate it at the point at alpha equals 0. This would be after evaluation, this would be the gradient of because when we dip the function, right? When we dip the function, the results of derivative would comes as the it would be, well, the basic derivative for this one. It would be the would be something like this is fx plus alpha u, right? So when we take derivative of this function, what we would have would be because this function contains input of alpha and u, right? What we have here would be the alpha curve by curve alpha of x, right? And then diff of the inside, and for the inside the parenthesis contains x and the alpha u. Usually when you take partial derivative, the one that doesn't contain the element will be treated as a constant. So the remaining of this one would result in just u. So that's why in here we have equal this, and then this become u transpose when it comes first, and then the because alpha approach 0, this would be the rate of change of x and fx. So using chain rule, what does it mean by this? It means that when we calculate the partial derivative of certain parameters, it can be evaluated as the rate of change of the function, and then multiplied with the change itself when the change multiply really small value. And then if we want to minimize f to find the direction of f, whether f is which direction that f is in that f goes to, whether it's decrease to a certain direction or increase to a certain direction, which direction is has the fastest decrease or increase. We can find that we want to find u. Right? The idea here is to find u, and u would indicate the direction that this goes, right? That it would go to. So to find that, it comes from calculating u transpose here and the rate of change of f by x, and then try to minimize it with respect to the constraint. And the constraint is that ut times u equal 1. This is because this is a unit vector. So when you find the size of the vector is actually 1 when you dot them together, right? So this minimization is the same as minimizing the size of u and the size of fx and cos theta. Why is that? Because the multiplication of the unit vector and the gradient by fx equals the dot product between the two vectors. Okay, and the dot product of the two vectors is the size of the first vector and the size of the second vector, and the cos theta, which is the angle between the two vectors, right? So we know that this size of u equals 1, and if we ignore the other factor, right, ignore factor that do not depends on u, because we are talking about u, then this would also be 1, and that would result in cos theta. That we want to minimize u so that so that the cos theta would be minimum, right? And what does it mean by having minimum cos theta, right? Having minimum cos theta means that we have the what values that results in cos theta that at its lowest between two vectors. So if you think about it, cos theta could be go into minimum value at -1, right? At -1, and that -1 is the cos of 180 degrees, right? So what we want to find, what we want to minimize, the result of minimization is that the u has to go to the cos of 180 degrees. It has to go to the other direction of the gradient. So what does it mean by the whole thing that I'm trying to show you here? This is the proof of gradient descent. That is, if you want to find the minimum value of the function, right, you need to select the unit vector that goes into the opposite direction of the gradient. Okay, and that would make the function goes to the minimum value. We want to find this, and that's why we start with defining u, which is the direction vector that we want to go, and u associated with the gradient by that, because that's the direction we want to go, and we kind of make a minimal change. This is fx plus alpha u, right? And then we evaluate it. What if we make change just a little bit by this alpha, and then this alpha would approach 0. Okay, and then we want to minimize this, because we want to minimize this f, the whole thing, objective function here, so that we have the lowest gradient. Lowest gradient means 0, right? Having the value of the lowest gradient, this is like absolute lowest gradient here. So it tells us that the lowest gradient can be achieved by having u going into the opposite direction of the gradient. Okay, so this is the proof of a gradient descent. Or if you want to think about it in a simpler term, this is more the mathematical term. In a simpler term, if you want to go down the mountain, right, you're standing at one point, you want to go down the mountain, well, you look at the left hand side. I don't know if it's your left hand side, this is my left hand side and the right hand side. And then when you look at the right hand side, you see it go up. Left hand side, you see it go down. And you want to go down the mountain. Which way you want to go? Maybe you can take. Oh, it's the opposite. Is it necessary for the U to be a unit vector? Well, in mathematical foundation, it is. But it doesn't matter actually. We define U as unit vector because in the end you can see that once we substitute U with 1 unit vector, right? Then the remaining is cos theta. But if it's 2, it doesn't matter, right? Because just factor. It's just a scalar factor, it doesn't matter. This just tells you that the gradient, the direction that you should go should be 180 degrees from the gradient. It should be the opposite side or the minus value of the gradient. Right? Let's see how it works in the algorithm. Now, say we have this form of equation, the function, in the nonlinear sense. Nonlinear sense means that it is quite hard to write an equation and then solve it by using like the least square method that we used earlier in the review, using linear algebra to solve equation, and that cannot be done with the nonlinear function. In the nonlinear function, we have parameter beta somehow associated with x. Okay, and say we have a simple terms here that beta is p times 1 vector, right? Unknown parameters with the size of p. And epsilon is uncorrelated error. Right? We have the error here. And y comes from this fx beta plus epsilon. And then we're trying to minimize this nonlinear function. All right. And in our data, usually we would have a set of x1, x2 to xk for each observation y. That means for y, the first y0, we would have x01, x02 to x0k. For y1, we would have x11, x12 to x1k. So we have multiple observations coming in. And these multiple observations can be used with fx beta to make prediction. Now, if we want to define the objective function, in order to estimate the best value of beta, we would put that function in comparison to yi. Why is that? Because yi is the actual value. fxi beta is the predicted value. By comparing them together, you get errors. And this error square, this means the square error. Right? This is the square error, is the error form that doesn't contain the sign, right? Unsigned form. Then combine them together, we have this sum of the square error, which can be used as the function that you want to optimize in order to find beta, right? For this one, S beta, you want to find beta that minimize this function, right? If you find a beta that minimize this function, then it is the goal of parameter estimation. The problem is, in nonlinear objective function, sometimes you have the surface, error surface, that is quite complicated, where you can have a point like this one, which is minimum, right? You have derivative equals 0, but it's not actually the lowest point. You may have this point, again, minimum, but not actually the lowest point. Or this one, which is the lowest, or you can have a saddle, also have 0 gradient. Right? Or this one, at this point, 0 gradient, but it is actually a maximum. So just the error plane is quite complicated, and it cannot be solved with just one goal. And on the other hand, you may have an equation that is not solvable, like the root. For example, if you take derivative of e to the minus x, you always have e to the minus x. And when you equate this derivative to 0, there's no solution for that, because e to the minus x would reach 0 only at infinity, which makes this a trivial answer. Okay, so it means that in a linear objective function, it is hard to just find the solution in one go. So how do you find the solution then? Then that's method called gradient descent. Okay, gradient descent, or some in some reference, this method might be called hill climbing if you want to go up the hill. But let's say we are trying to go down the hill, right? We are going to descend on the opposite side of the gradient. Okay, so the idea is that suppose we have this function fx, and we want to find the lowest of the function. We can randomly start at any point here, right? Randomly start at any point. Let's say start at this point. Afterward, we can iteratively go down this slope by finding the gradient at this point. This gradient is this is from the of fx by dx. Right, this is the gradient at this point. And then we can go to the we can go to the next value by updating this gradient by going down. How to go down? Right? Since we already know that this the black arrow here is the gradient, we can just take a minus value of this gradient. The minus value indicate going into the opposite side of the gradient, right? And then multiply it with a very small alpha. This very small alpha indicate the learning rate. Right? You want the step to not be too large. Right? You want to move step by step until, and then guess the new gradient, and then keep doing that until it reach right the end, and it reach the point that you need to stop. But what would happen if the step is too large? Say if you say the very last step, this can happen, right? If the step is too large, and say we start at this point, you may end up with something like going into the other side, overshoot into the other side, which is not good, because that means your solution might keep getting worse, going up, right? It might be trying to go down, but you can still see that this is not a good way to go to the solution. So in the usual practice, the step of the gradient would be a very small value, and then you try to iteratively go to the solution. But this is also a problem, especially in deep learning, because we have such a huge network, and this network need to be updated. If the step is too small, then what would happen? It means it would take very long time for the system to learn, and many techniques in deep learning try to address this issue by having the step size to be adaptive, having the step size to be less conservative, accepting more gradient, creating architecture that would receive gradient easier. You can see that further architecture of deep learning try to deal with this issue of gradient descent. It is inherently from the optimization method itself. Okay, so maybe I guess in the future, the advanced research in deep learning would go towards something like a new method for finding a better optimization or optimal values for the parameters. Right. Okay, so here how the algorithm works. Starting from randomly guessing the point, okay, this point, and then the algorithm will repeat this step. Determine the descent direction. So after we randomly guess the point, we can estimate the gradient which go up, right? The gradient of this point would go up. Let me draw the gradient here. The gradient itself would go up, so the direction would need to go down, right? So determine the gradient direction, and then choose the step size, and then update. Choose the step size and update the value. So now our solution is this point. And then repeat the same thing, right? Determine the descent direction, choose step size, and update until the solution reach the terminal condition. Right? And that terminal condition is quite tricky. Well, in this figure it's not, but in real life, especially when you train deep learning model, this is very tricky because you can have a point where when you improve your network further, it improves the model for the training dataset, but it does not improve the result in the testing dataset, and that is called overfitting. Right, so this is quite tricky. There are multiple ways to address these overfitting issues. Some of that relate to optimization. Another is trying to find creating a better input, or some would involve with the architecture itself. We will see this regularization of the network in the next lecture. Okay. All right. So and actually in your assignment today as well, you start doing the regularization with your model starting from today. And if you have worked with machine learning before, you may have tried something like decision tree, logistic regression, gradient descent, linear regression. Well, you implement it from scratch today, including the additional condition, which will be fun. I guarantee that, right, from the last year comment. All right, so this is how it works in the pseudocode. So starting from randomly guessing the point in the model means randomly guessing the beta, the parameters. Once you got the beta, and then go to the loop, start with determine the descent direction. That means you need to have the gradient, and that comes from the derivative of S beta, right? The error function S beta is the error function, take derivative of it with respect to beta, and then go to the direction of minus, the different direction of gradient. And choose the step size. Usually this is chosen as a fixed value if you specify that, but many algorithms would adjust the step size depending on other things, right? Depending on the direction, depending on the previous gradient, depending on the momentum. So there are other methods that relies on multiple things to adjust the step size of the gradient descent. Then the updating of parameters would be to adjust the old parameters, and then adjust it by taking the step toward the negative direction of gradient. So basically you just multiply step with the direction and then subtract, or I would say add it to the actual parameter, the existing parameter. So this would supposedly make the parameters go into the opposite direction of the gradient, or of the error gradient. And finally, we will stop once we reach the satisfied criterion. This satisfied criterion can be that is the gradient approximately equals 0. That's one criterion. But it can be the others, like you have the lowest, or well, like usually it will be like you reach the maximum iteration that you specify, maximum epoch that you specify. So that can be the ending criterion as well. Okay. This is how gradient descent work. Okay. So it works by randomly guessing. It works by iteratively determining the direction. Okay, I will draw it again. The function. So start from step 1. You would randomly guessing the point, and then determine the direction. This point, go into the opposite side, choose a step, update means that you move the point to the new one already, and then do it again until you reach the end of the optimization and reach the final goal here, right? This is gradient descent. Now we'll see how gradient descent work in the model, right? We'll see how it works with the example of logistic regression. All right. Okay. Let me switch from this. I have multiple slides that derive the solution, but I will write it on my iPad, and then you can follow through. And the note on the, and then the note in the slide, you can look at that if you want to review if you want to review what we learned today later on, right? Because if you just look at the code here, it is quite overwhelming. A lot of things here. So I will just not talk about it yet, and then we'll iteratively derive it together. Okay, we have one question coming in. Do you have example of what is the meaning of stop until the criterion satisfied? Okay, let's take a look at that first. All right, say at this, let's look at this algorithm. Okay, what can be the stopping criterion? Criteria. Okay, the first stopping criteria that can occur is something like the gradient, right? The curve of S by curve beta. This is approaching 0. Right, this is the first criteria. So if this condition is reached, the algorithm should stop, right? Because you probably reach the lowest point at this location, because this location gives you no gradient at all. Although in some condition it's not true. All right. The second possible criterion is that you have something like this one, the maximum iteration is reached. Now you have reached the maximum iteration, and that could be you need to stop as well, or in a complicated way that you can write in Keras in deep learning, you can define it as you have this testing error, going up, and training error going down. This can be a criterion as well, and then you probably need to stop at this point, because if you find after doing the optimization, and you find that the more you optimize the model, the more testing error increase, right? The optimization increases in testing error while reducing the training error. This is the condition called overfitting. Right, this is a condition called overfitting. Yeah, so these are the stopping criteria that can be used in order to stop the optimization, stop the loop. Right, so repeat until the stopping criterion is satisfied. I mean, that's, well, whatever, it can be any of that. Mostly the one that is often used is the second one. What will happen if we have 2 or more 0 resulting value? What values? What do you mean? You mean 2 or more location, 2 or more local optimum, right? Okay. So what if we have more than one? Like this one. Now, if we take this part, we will be unfortunate, right? But if we go to this one, or we have a chance to jump across, well, that might be better, right? So the optimization need to balance between two things. The first is called the exploitation, right? If you are interested in optimization, I would suggest you take the optimization course. It will go into more detail about the optimization, including interesting algorithms like genetic algorithm, simulated annealings, and others, stochastic optimization. I think I find it very useful in my research career afterward. For now, I'm going to just explain how the optimization work in this sense. Using optimization, we need to balance between two factors. First is the exploitation factor. And another one is exploration factor. Exploration. Right. You need to balance between exploration and exploitation. Exploitation means going into the direction that will become greedy. You want to go into the direction that will satisfy you the most. Right. So that is the direction that you go, like going down here. This is exploitation. But you want to balance it with the random, right? The randomness that allow you to explore. You want like reading. When you read, you may have a goal, and if you read to the goal, that's exploitation. But you will learn just the thing that you intend to learn. But if you also read random books, read the books from social, read the other thing, that's exploration. You can broaden your knowledge. So think about this as a research career. So if you want to take your research career right now, because you are a graduate student and you need to consider about research, if you just have a problem in front of you and then you try to just solve that problem, that the thing that you learn from the process would be just for that problem alone. But if you also learn the broader sense, if you also learn the research related to the work that you are doing, if you also learn about the application of the work that you are doing, then your learning of the concept would be broader. And then you can also jump past the plateau, jump past the stagnant if you ever find one. Like maybe you can try to instead, like for me, for a while, instead of working on the speech, I switched field to work on mathematics. So that I can broaden my perspective. I switched the field to work in the medical engineering. And that can open my eyes to see multiple model or the same model applied to multiple tasks. And then I switch again to work on the data from companies, from big data and data science. And you can see that there are like similarities and discrepancy between them, and that's exploration. In optimization of the problem as well, you want to balance between exploitation and exploration. And that is actually the key of your assignment today. You need to balance between them. Right? Exploitation means going to the same or the direction of gradient. Yeah, this is exploitation. But the original algorithm lack of exploration, which I will introduce you at the end, and then you need to do it in your assignment to do the stochastic gradient descent. Stochastic gradient descent. So that's the name suggests. This is like the algorithm has to be able to jump past the cliff here and go down to the direction that it need to kind of be able to shake off the lowest value and then go into the direction that you need to explore. Okay, one question coming in. What is like? Could you please repeat the criterion to check for overfitting? Right. Well, a simplest criteria is that testing error go up. Right? Say you have a graph like this one. Well, you will learn this later on in the regularization, but never mind. Let's talk about that. So here, this is usually this is the what should I call? The model complexity or the complexity of the model. This includes the number of iterations that you train the model, and say this is the error. Right, the errors from comparing the data with the actual data with the model generated data. Black line here would indicate the training error. It goes out. While if you have the testing set, it will go like this and then go up. It is the testing. Usually it is the case. So it means that after increasing model complexity to a certain point, the model wouldn't be able to generalize. It wouldn't be able to work with the testing data. You can see that it works with the training data, but after you increase complexity, increase like model iteration, epoch of learning, or increase the number of parameters to be more than enough, then it start to fall down. How does this happen? I have a one good example here that is like it, that is easier to understand than think about the training and testing here. Think about you know your friends, and your friends these friends when he or she prepare for the exam, he would read the book, she would read the book, and then read just that book. But at the end, when the exam come out, the exam is quite generalized, and that person might not be able to apply the knowledge, right? Apply the knowledge because read just one book cannot apply the knowledge to because just remember that book doesn't mean that you can apply the knowledge to the exam. On the other hand, you may know another person, right, that read just a few books, skim around, but he or she can apply that knowledge, and that means the difference between this overfitting, this area, this is overfitting, this is underfitting, and this is just about right. You want the model to be a little bit overfit, but about right. So it's around this area. Okay. Good. Yeah. Let's move on, because we'll now take a look at a more complicated stuff here. Right. So my more complicated stuff is actually a very simple model. This model is called logistic regression. Logistic regression model try to separate the two data into two parts, right? One by separating it by line. So the idea is to find a line that separate data into two. Okay, find a line that separate the data into two parts. Okay, and you know that the line is usually defined as y equal mx plus b, right? So we want to find that line, and that line will separate the data. In logistic regression, we usually denote the distance between, say, the distance like this and this one from the lines to the, because you can see that if we just draw a line and then find the distance between the line to the point, this distance has the range of minus infinity. Let's say if it goes in this direction, it is minus, in this direction it is plus, right? So the range of the distance is minus infinity to infinity. However, in the logistic regression model, we are modeling the binomial distribution of the variable, right? Or if we talk about last time, we are trying to model the Bernoulli trial, right? That means the output can have two outcomes, 1 or 0. Okay, it can have success or fail, right? Because it has two outcomes. Instead of and it has a chance of 0 to 1. It works like probability. Right? You want to explain the chance that one thing would happen, like throwing a coin and you get head, as a probability, right? But if you look at the regression, it means that you reduce things to say a line here, and then you are trying to tell whether this point should be above the line or below the lines. The distance between the line and the points are not probability. You will probably have certain value here, right? Negative value and positive value. How can you bridge between the distance to probability? The mathematician has the answer for you. Right? You can explain this as the proportion. You can explain this as the proportion instead. So we can explain logistic regression has this formula. This is the line equation, zeta 0 plus theta I xi and then sum it from I equal 1 to n. And instead of having just these line equations alone, we can associate the output of this to a proportion between the two. This is the think about h theta x as the output of logistic regression. So we have this probability of belonging to the class, and this is 1 minus probability of belonging to the class. So the division between them creates something like the odd ratio. This is the odd ratio, or the proportion of the belonging to the class and not belonging to the class. Okay, so the logistic regression is in this form, and we want to find the best value of this theta 0, theta I from 1 to n, that are best optimized for predicting the probability, right? Predicting the probability of the class. This h theta xi is a logistic function 1 over 1 plus e to the minus fx. It has the curve, I think, next page, no? It has the curve that looks like this. So this function, if the value is in the positive side, say fx is more than 0, this is h theta xi. If fxi is more than 0, say if it has very large value, if it has really large value, you can see that e to the minus really large value equals 0. Right? This value would approach 0. And if this value approach 0, it would h theta x would have value equal 1. This is 1. And if this fx is 0, right? If this is 0, then you have the value here equal e to the 0, which is 1. That means this is 0.5. And then you actually have this graph. If fx has the very negative value, then this logistic value, the logistic function value would approach 0. So in this case, you can now map between the probability of belonging to the class and the distance that occur in the distance that occur in the line, right? So we can map the two together. This is logistic regression. Okay. Now we will take a look at how can we optimize the parameters theta so that it would separate the class, given that we have certain value of x, and we have the Bernoulli distribution, or to tell whether this xi have the value of yi equal 1 belonging to the class, or 0 not belonging to the class, right? So this is usually the binary classification job. Okay, now one good thing about h theta x, one good thing about h theta x is that it has a certain nice property, that is the derivative of the h theta x equal the multiplication of the two. Why is that the case? Let me show you in this in my iPad here. Let me share the screen. I need to share the screen using Zoom. Share content. Cannot share. Need to allow to share first. Stop sharing here. Then start sharing here. Need to share the screen or whiteboard. Okay. All right. We have the h theta x equals 1 over 1 plus e to the minus fx. Alright, then what we want to find is, and we know that fx equals theta 0 plus summation of I equal 1 to n of theta I xi. This is fxi. I will drop the subscript. It's troublesome to write. Okay, so we know the hx, that is the logistic function, looks like that, and we know fx is the linear combination of input and parameters. Then we can find the partial derivative, right? The partial derivative of hx, h theta x by curl theta. And how do we take derivative of this one? We will just think about this as curl by curl theta of, say I would write it in another form, 1 plus e to the minus fx. Okay, how to take derivative of this function? Oh, sorry, this is minus 1 as well. Okay, how to take derivative of this function is just a simple calculus 1 again, right? So we need to put 1 down. This would be minus 1 down, and then 1 plus e to the minus fx to the minus 2. Right? This is the derivative of the whole thing, the parenthesis. And then we need to take the derivative inside, right? Curl by curl theta need to go inside the parenthesis. It need to go inside the, say, you see my, no, you don't see that. How do I annotate at the same time as talking? Let's see annotation tools and mouse, right? No, the arrow would do. Okay, so here we need to take this derivative and then put them inside here. Okay, that means derivative of this of 1 would be, because the derivative of constant would equal 0, so that makes the first element here 0. But the second element, the derivative e to the minus fx would be e to the minus fx. Right, so the derivative of this e to the minus fx would be e to the minus fx, and then the derivative of the inside again. Okay, the derivative of this inside would be minus curl fx by curl theta. Okay, it will be curl fx by curl theta. Now let's see if you see here that the theta here, theta 0, if you think about it, you can think about it like this. Theta 0 is actually having input equals 1. So when you take theta here, it's just like you are trying to calculate for any theta I, or for theta 0 is like x0 is equal 1 anyway. So we talk about theta I. Okay, so that means the inputs here, the curl of fx by curl theta would equals xi, right? So the result is plus xi. So write it again this way. We would have this equal. Let me clear this out. How to clear annotation? How do I clear the annotation out? Clear all drawing. Oh no! Undo. Okay. Yeah. Right. Let me arrange this equation a bit. Right. Here you have this e to the minus fx over 1 plus e to the minus fx square. And here curl fx by theta, this equal xi. Alright, then we can separate it into two parts. The square itself is 1 over 1 plus e to the minus fx. This is the first part, times e to the minus fx over 1 plus e to the minus fx, because it is multiplication between two parentheses, and then xi. Alright, so we have the first one here, which is fx. Right, the first one, let me put the annotation again. I don't know if you see my mouse here or not. I don't see it here, so I suppose you don't see it as well. Right, maybe you should use the arrow. Right, the first term here is the same as h theta x. Right, see the similarity here. So that means the first one is actually h theta x. How about the second one? Right, it looks like h theta x, but it is actually e to the minus fx. Surprisingly, e to the, if I were to rearrange this e to the minus fx over 1 plus e to the minus fx. Well, how do we rearrange that? Well, consider this term, 1 minus 1 over 1 plus e to the minus fx. This equal, if I multiply it up, this is 1 plus e to the minus fx minus 1 over 1 plus e to the minus fx. And this equals e to the minus fx over 1 plus e to the minus fx. Alright, so they are the same. But what is the left hand side again? This one is actually 1 minus h theta x. So it means that this thing is h theta and x, and for this xi, and this is 1 minus h theta and xi, and times xi. So surprisingly, the derivative of h theta x is simply the multiplication of the values. It means that if you already know h theta x value, you can just multiply it with 1 minus h theta x, and that's it, right? This is very interesting properties of the sigmoid function, of the logistic function, that you can calculate the derivative without having to do the derivative itself, right? You can use multiplication to do derivative, and this allows us to speed up the calculation a lot. This is the way that it is done in neural network back in 1990. Right? This is called one of the method called backpropagation in the original version, using this instead. In the latter improvement of deep learning approach, people now skip past just having sigmoid to a function that is faster to train, so that you can use the computer to learn the function faster instead of this one. But in the property itself, it still reflects on something that is in deep learning. You want the function that is easy to calculate the derivative, right? The derivative has to be easy to calculate, so that you can use that to optimize the model. So maybe, I don't know, in your research later on, you may invent the new activation functions, and that is easy to calculate here and optimize faster, right? When you review your research in term paper for this course, you may see lots of work that try to address this issue. All right. So this is how you take derivative of the loss function. Now let's go back to the slide. All right, there's question coming. will we need to calculate using this formula in exam and assignment? Well, yes. in assignment, yes. Right, you need to do derivative like this one for the stochastic gradient. This is just a simple gradient calculation of the activation function. But the one that you need to do is a little bit more complicated than that. Let's take a look at the thing that you need to do here. Let me stop the sharing, or I can just switch, right? All right. Okay. So that is how you calculate it has the nice property of the function. That is, the derivative of the function is the value of the function itself multiplied with 1 minus value of the function multiplied with input. So this is the one that is incredible for the logistic function. And it's good in learning, because in learning you can see that gradient descent requires the calculation of derivative. But you do not have to calculate the derivative. You just need to calculate the value, then multiply with 1 minus value for the logistic regression. Now, this is just for the function. But in order to find parameters, right, what we want to find, the aim of our work here is to find parameters. Right. We want to find the parameters, right, that minimize loss. Right. We want to minimize loss and find parameters that minimize loss. Right. So we just consider the nice property of sigmoid, but the actual loss function is not the sigmoid function. For logistic regression, we can use the binary cross entropy to explain the loss function of the logistic regression. Let me explain this equation a bit. All right. So just think about the situation that you have yi equal 1. Say you have yi equal 1. Class 1, that positive class. If you have yi equal 1 and the model is good, right, good model. In the good model case, your h theta, I will just write as h theta, okay? Your h theta would have value approach 1. Right, this is good model. Right, the values would approach 1. Right, in bad model, say h theta would have the value not approach 1. Well, it can approach 0.5, it can approach the other way around, it can approach 0, it can approach the value that is not 1. That's the bad model, because it cannot capture the pattern here. Let's say it's 0.5 then. Consider this case. So this is the loss function. J theta is the loss function. So if in this case yi is 1 and we have a good model, what would happen to the loss function? We would have this equal 1, right? Yi would equal 1, and then the log of h theta xi, right? If h theta approach 1, what would happen? What is the value of log of 1? What is the value of log of 1? 0. That's right. So that means in the good model case, this would approach 0. And if the value approach 0, that means this term would kind of approach 0. Right? If in case of the good model. In the bad model, and the second term, right? 1 minus yi, because yi is 1, this would be 0. Okay, that means we consider only the first terms. Okay, now in a good model, again, let's say, well, in the good model, if yi equals 0, then h theta would approach 0. Right, good model case, yi is 0, the first term becomes 0, and this is 1 minus yi, which would be 1, and this is log of 1 minus h theta, and theta approach 0, that means this would approach 0 as well. So in the good model case, the loss would be approximately on either side would approximately be 0. Right? This is called cross entropy. Now let's consider the bad model case. Right? The bad model case, say if the h theta equal 0.5, right, cannot decide whether it would belong to which side. What would happen? In y equal 1, right? This is if y equal 1, then we consider just this model. We have log of 0.5 in the case of this, or maybe 0. What would happen, right? This is 1, and say we have a very small value, right, on the wrong side, say 0.1. The log of 0.1 will be certain negative value, right? This would mean that the log here in the bad model case, the log here would be a certain negative value, like a negative some chunk, and then this chunk multiply with this yi, it will result in certain positive loss, right? So in the bad model case, you can see that it will incur some positive loss because the negative of the wrong side probability would be multiplied with minus value here and incur the negative loss, the positive loss. And the same go for the second one. If the result is 0 and we have this like on the opposite side, you get a chunk of value of loss there, right? So we call this the binary cross entropy because it relies on the entropy function. Right? Anyone, if you are study the information theory, you may have seen this in the calculation of the Shannon entropy, that the Gibbs entropy, that use the mixture, the probability as the indicator to which the class is mixed or not, which is class or not. Okay, so that means we now have the equation for the loss function or the error functions, and our job now would be to take derivative of this function, right? Taking derivative of this function with respect to theta. Okay. All right. Actually, I have two choices for you guys. Whether you would just let me just take derivative, or you would just let me explain on how to do that. But let's see. Maybe I need to check the number of slides left here first. I'm now at slide number 26. I run out of time. Okay, so I would just go into the next slide and then explain from that instead of deriving it myself. Okay, so here's how you take the derivative of j theta with respect to theta, right? So I outline here in the step by step, and I'm going to explain it step by step. If you do not understand or you want to review this, if you do not understand, please ask. I will answer that immediately. If you do not, if you want just to review it because you cannot catch up, you can see this in the video later on, right? As many times as you want. And if you have questions afterward, you can just post in the group. I'll be happy to answer that. Okay, so start with this loss function. Right? We have the loss function here inside. Then we want to take the derivative of the loss function. This is the first line. Right? We are taking derivative of the loss function. When you do derivative, just do it step by step. Right? Starting from a simple step like moving in and then try and do it step by step. Otherwise, you will kind of become think of it as confusing, right? When I do the math, I will often do it step by step and then apply the rules. But I think the problem that many of you may be facing is that you have already forgot the rule and how to use that. So, well, work on deep learning would require you to understand this, I guarantee, because many times I read the research paper in deep learning, it go even deeper than what I show here. Okay, so, revise your skill in calculus, right, and linear algebra. You'll be you will definitely be able to now realize the use of you will realize the answer to the question that you have maybe 4 years ago on why do I have to learn these things. Now it's time to make it for the use here. Okay, so here the partial derivative of the loss function by theta. Okay, and you can see this is sigma, right? The summation, which is the linear operator. You can just move the curve by curve theta inside the summation. Okay, moving it inside the summation would be like moving this curve by theta into the first term and the second term. And you can see that because it's curve by theta, yi doesn't mean anything. So it means just like some constant value. We can just move it to curve by theta of log theta and xi. Same goes for the second one, which is curve by theta and log of 1 minus theta xi. Right? And derivative of log is actually, what should I say? Well, if you take the derivative of, say, d of log fx by dx, this equal 1 over fx and dfx by dx. Okay, so this is how you calculate the derivative of the log. And so here for log of h theta xi, I just put h theta xi to the denominator here, right? And then this would be the derivative of h theta xi, and I just leave it at that first. And then do the same thing for the second one. This is 1 minus h theta xi because this is 1 minus h theta xi. And then derivative of the partial dip of the 1 minus h theta xi, and the second term. Okay. Now for the two, we need to still go deeper, right? Take derivative of h theta xi. This is simple, right? You know that it is the multiplication of the active two sigmoid, right? The one sigmoid and then 1 minus sigmoid and then xi. We did that in the preceding slides. And the same thing, right? And for the second one, this will be a little bit more complicated because you take derivative of the inside and it has minus here. So that's why when you take derivative of the inside here, you end up getting h theta xi, 1 minus h theta xi, and minus xi because you have the minus value here. Okay, this is the now on the fourth line of the equations. Okay, and then we need to rearrange, right? So working on mathematics, partly doing the math itself and partly rearranging it so that we have a simpler, more generalizable form. Okay, so how do we rearrange it? The simplest way is to break it down. So what I did here is to break it down, right? So you can see that here, h theta xi and h theta xi, so it cancel one another out. I can just use this one instead of using that. Also, it cancel each other out. The same goes for this one. Cancel each other out, and that's why we have yi and 1 minus h theta xi and xi. And the second one would be 1 minus yi minus 1 minus yi and h theta xi and the xi minus xi here. Okay. Then again, rearranging things, which means that you need to pull xi out so that it kind of going out. You can summarize the inside here. So once you pull this out, xi would go out, and this xi would go out, and minus would now make this symbol become plus. Right, and now we are here. Now, if you don't know how to summarize it further, just multiply things in. Right, multiply yi inside, multiply 1 minus yi with h theta xi. So here you have yi multiplied by 1, you get yi. Yi minus yi multiplied minus h theta xi, you get yi h theta xi. And the second terms, h theta xi multiplied by 1, you get h theta xi. And then minus yi h theta xi. Multiplied together, you get minus yi h theta xi. Now you will see this term cancelling with this term because here is minus, here is the plus. And finally, the result is the gradient of this one is h theta xi minus yi and times xi. are very simple terms here because h theta xi is the output of logistic regression. So what does it mean? It means that the gradients come from the difference between actual output with the predicted. So this is the difference between the predicted and the actual, and then multiply it with input, right? And then sum them all together, you get the gradient on these parameters. Okay, so you can see the step, although it's quite complicated, but the result is quite satisfying. It's very a simple notion that you can just take the derivative with the delta, then multiply it with the input, and then you get the gradient. All right. And now we know that the gradient equals this term. We can just use it in the gradient descent by updating theta k with minus, mean that the opposite direction of the gradient of the j theta by curl theta, and multiplied by the step size. This is the step size. Step learning rate in this case. And then put it in, you get this equation. We can now use this equation to optimize the parameters of the model. Okay, and the initial parameters, the theta 0, because you can see that this is theta k plus 1, the iteration k plus 1 comes from iteration k, and then adjust it a bit. Now it needs to have the starting point. The initial parameters can be randomized, right? Or it can be any values, because the last one is convex, so that means it can be any value, and just randomize it out. Okay, this is the result. I implement it on R here. In your assignment, you can choose to do this on any languages that you prefer. Python would be okay. But if now you are not familiar with Python yet and then you want to use other language, I'm fine with that for the moment. But note that later on when you do more on the deep learning, you need to use Python anyway. So I would encourage you to use Python starting from this. So initially I randomed the data into two classes like this one. And then you can see the gray bar here. Initially gray bar looks like this one. The reason that it changed, this is because in each iteration I perform this. So just update the parameters with the difference between the output and yi and time with xi. Then sum them all together and then use it as a gradient to update the value of the parameters. That's it actually. That is the result that I got. And you can see that the line adaptively changed the slope and the intersect on the axis, so that it would separate the data into two parts. This is the result of the learning itself, of the learning process. All right, let me take 5 minutes break, and we will come back. We still got a number of slides to go. Okay, I'm back. Let's move on. We still have a number of contents to cover here. Right, as you have seen now the gradient of logistic regression and how you can derive the gradient of the logistic regression from the loss function. Okay, now you can in the gradient descent of logistic regression, you will see that the error function itself contains only only the loss function about the error. So this is about the errors. The other one is also about the error, the mismatch between the data and the model. Okay, but sometimes we wish to not just minimize the function. We need to have something like the maximum minimum values. We want to have something like constraint putting into the objective function. Like it can be the range of the value, it can be the weight of the weight that you want to use. You want to minimize them. It can be the number of parameters that you want to use. This is known as constraint optimization. Known as the constraint optimization. Optimization with some constraint. In the optimization with some constraint, usually there would be a feasible region, right? Feasible regions are the region that the solution, when it lies onto those regions, that they are feasible. Okay, we need to usually define the constraint, and then the optimization has to find the value that fit into the constraint that we defined. Let's take a look at a simple example here as a line search. In a line search, right, we can you can think of this as think about gradient descent as taking a line search with constraint into account. So we can just say we have the boundaries in the blue lines here, and then we search from one value to another value only in the value within the regions. Okay. Now, if you think about this, right, we now have like the region that the value would be valid, and this allow us to convert the constrained region, right, into the unconstrained optimization. So the idea is that instead of having constraint that define as the limited point here of the optimization, we can convert the constraint, or in some case we do not have explicit region, we just have certain expression that we want to convey, like we want the parameters to be small values, and that is hard to define the feasible level of the solution. Like, well, what does it mean by small, right? In that case, we need to convert that into the description in the constraint base into an unconstrained optimization. Okay, how to do that, right? We need to think about the term of the loss function. The term of the loss function can have a part that related to the equality constraint and another part that is related to the inequality constraint. Okay, and we have a part here, the loss function, that relate to the model. This is fx. Fx relate to the model, just like the one that we consider in logistic regression. But if we want to put constraint into the loss function, we need to put it into the loss function. And then just we have the cross entropy here. We can add in the equality constraint, the summation of equality constraint. This has to add up, and this can be the equation about the inequality constraint, that if it is not equal, it is more than the value, then it would generate loss, right? So just remember that any function that you put into the terms, it has to have certain expression. That is, the more the worse, right? The more the not good, right? Because this, you can see that here, higher value of error, certain mismatch, right? So in this, it also need to indicate like if the equality function is incorrect, right? If it's not equal to the specified value, it has to generate large amount of error. So something like comparing exactly to a certain value that would work, and it's squared. So you can do that. And this one is inequality constraint. Inequality constraint indicate the constraint like the value has to be less than certain values, and then you can define the function to express it in that sense. Okay, let's take a look at example. Maybe you will have an idea here. Let's say that we want to minimize this function. This is fx equal 1 over 2, and then this is ax minus b squared, right? We want to find the value of x that minimize this. Then if we consider the gradient of the function, okay, consider the gradient of the function. The gradient of the function is the derivative of this one, meaning that putting 2 down, then it will cancel each other out, and then we have ax minus b. Ax minus b and then curved by x means that we would have just the first term. We get the first term out here because this is the matrix calculus. It's like with respect to certain matrix with a certain vector, you get the whole matrix out to multiply with the whole thing. So we got this as A transpose and then the ax minus b. And this A transpose multiplying in, you get A transpose minus A x and minus A transpose minus B. This is the gradient of this curve x by fx, curve fx by x of the linear regression. Okay, we want to minimize that fx. All right, we want to minimize this fx. If we minimize this fx, we would get the value of the unknown parameters, right, of x vector that is best satisfy the function here. Okay, so this is like what we did in linear regression. But instead of just that, we want to specify the constraint, right? And this constraint, let's say we want the constraint to be that x transpose times x less than or equal to 1, which means x should be a unit vector. Or, in other words, we are trying to say that whatever coefficient that we estimate should be low value. The value should be less than 1. You cannot get the value like a very large value here. Okay, how to express this in a sense? So if you take a look at this and then move 1 to the left hand side, we would get this equals x transpose times x less than or minus 1 is less than or equal to 0. So it means that the larger discrepancy, right, between this one has to be less than or equal to 0, means that the latter one has to be less than 1, basically, because if it is more than 1, then it would violate this one. So we can put this into a constraint like this. And this is the terms that it needs to be less than 0, right? It needs to be less than 0, and loss should be less than 0. And then multiply it with lambda. Lambda is the parameters that would control the proportion between the constraint and the main error. Then now our task from the constraint-based optimization has turned up to be the constraint optimization, the unconstrained optimization, by finding minimize value, minimize this function. This is x, and this has to be maximize value of lambda, right? We need to maximize the value of lambda that would minimize L x lambda. Basically, we want to minimize L, right? Minimize the loss. Minimize the loss while having the minimization at the maximum value that we got lambda value, appropriate lambda value out. Right? And from this term, to solve this minimization, we can differentiating the above here, the loss function. Take derivative of the above here. So we get this, the derivative, we already calculate that. This is A transpose A x minus A transpose B. This is this one, right? Curve fx by x here. And the derivative of the second term by x is, this is like x squared. So that means the remaining here would be just lambda x. Right? So it would be 2 lambda x here. Just like x squared, meaning put 2 down and then you get lambda x. This equals 0. Right? And rearranging this equation, meaning that you need to just put x on the same side, move A transpose B to the other side, and then calculating the inverse, because we can just pull x together. If I were to write it, it would be, let's say here, this would be A transpose A x plus 2 lambda x equal A transpose B. And then we can pull x out. Then you get A transpose A plus 2 lambda, and then x equal A transpose B. And x would equal to A transpose A plus 2 lambda. Okay, I forgot this. And then inverse equal A transpose B. Right. So this is the solution down here. And if you remember the pseudo inverse, in the pseudo inverse, we got only A transpose A and inverse and A transpose B. By putting in the errors from the constraint, we now introduce the new terms here to lambda I to this equation, meaning that it would add into the value of x a bit here. So the meaning of lambda here is the control of the constraint. So lambda must be chosen so that you have the appropriate proportion between the error, right, the errors of the constraint and the actual error. So how to find the value of lambda? We can take the gradient by lambda. Take the gradient by lambda, you get the value equal the x square actually minus 1, the second term, which means the gradients would be on the opposite side of the value of x. So so that is the way that when we consider, we can put the constraint into the loss function. And you see in your assignment that you have to also put the constraint to the loss function and then calculate the gradient descent with the constraint, right? Right, we will take a look at that in your assignment sheet. Okay, so that's how you can do it. But there are actually more ways to perform optimization, like this one. Because doing gradient descent using just first derivative alone is quite slow. So researchers try to think of a way that they can accelerate the optimization process. Just take a look at this. Okay, so if we have this line, this is y equal ax squared plus bx plus c. The derivative of this one would be 2, right? This would be the derivative of this would be 2ax. Yeah, I should write. The derivative dy by dx would be 2ax plus b. Right, 2ax plus b at this point. And if you take a look at this one, this x0, right, this x0, if we put the value x0 into this point, right, into this point, the x0, and then calculate the difference between this x0 and this point by equating this into 0. Say this equals 0, then we would have x equal minus b over 2a. Right? That means the lowest point here is minus b equal to a. That means if we have a particularly some point x0, the difference between this point and the lowest point is x0 minus b over 2a. This is the best step, right? And multiplying it up, this is 2ax0 plus b. Okay, what does that mean here? That means we can determine the best step by the above here. What is it? The above here. This is if we substitute x0 into the first derivative, right? So if we say the dy by dx and then say x equals 0, this would be 2ax0 plus b, right? The same as the above here. And what about down here, 2a? 2a is actually the result of, this is the first derivative, right? The second derivative is 2a of this one because x will be removed. And that means the best step is actually the first derivative divided by the second derivative, right? So this is quite interesting, and this is the idea of another method called the Newton method, right? So instead of doing the gradient descent alone using the first derivative, Newton method utilizes both the first derivative and the second derivative to update the parameter. Sorry, this is wrong. Right. This is theta k should be updated by minus alpha here, and then the first and divided by the second. So usually the idea is that it should go into the best direction, and this will be faster than going down the gradient, because gradient can be a detour while doing the second derivative as well, it would go into a better direction there. This is called the Newton method, which in the optimization that we will see later on, you will see that this has been incorporated into the algorithm that Keras, the algorithm and TensorFlow used in the optimization of the model. Now let's look at the last one. This one you have to do it by yourself in the assignment. This is similar to gradient descent. The technique is called the stochastic gradient descent. It is the same thing as gradient descent. The only difference is that you need to choose an initial vector of the solution. This is the same thing, but instead of using the whole dataset to optimize, you need to randomly select the data, the sample data, just a portion of data out, and then calculate gradient, do the gradient descent, update the parameter, and keep doing that. So the only difference of the stochastic gradient descent to the gradient descent is that instead of updating the parameters for every point of data, you need to just random a portion of data out, maybe, I don't know, depending on you whether you choose maybe 30%, 50% or whatever, right? Choose, you can randomly select a data set from the larger data pool, and then keep doing that, right? Repeat it a number of times until the minimum point is reached, or until you satisfy the certain stopping criteria. Stochastic gradient descent, if you perform it correctly, with the gradient descent, it could go in this direction, right? But with stochastic gradient descent, you kind of balance between exploration and exploitation. So it can go jump up out the loop, but in the end, usually it would end up at the lowest point, the lower point, better than the stochastic gradient descent, because it has ability to jump off the cliff. It has an ability to jump off the local optimum, and that is a good thing about this algorithm. Right. So now let's take a look at your assignment. This is all for today's content. Right. Let's take a look at an assignments. In the meantime, if you have questions, type in. Right. I will answer it right away. Okay, let's take a look at assignment. I will upload the assignment sheet tonight. Where is it? Should be here. Deep learning. Right, you got about 3 weeks to work on this assignment. Actually, initially I'm going to put it as 2 weeks, but because the 7th is a holiday, so I cannot do that, right? Yeah. So here is the gradient-based learning with regularization constraint. Okay. We will write an algorithm to learn the parameters from this. So you're still doing the logistic regression, which has the following formula, the same as in the slide, and HW, it's also the same as in the slide here. But instead of having just the loss function alone, now let's introduce this criterion. This is called rich regression. Right? Rich regression. By introducing the L2 norm into this, the effect of L2 norm of this W square, it would reduce the weight of the parameter. So instead of the weight being the value of arbitrary value, now the weight would be small value, just like 0 something or a very low value, instead of having a value very large value, which will be easier in multiplication in many cases. Okay, and it will reduce the chance of having overflow computation in the large value computation. So LW is the loss function, and lambda is regularization parameters. Here it's controlling the weight between the loss and the weight, right? And the rich regression would penalize the use of the weight. Right? So here, and you can download the iris data set in. It doesn't matter, just simple data would do, because what I want you to do is this. So you need to prepare the data to be one against the rest strategy. One against the rest strategy means that you are calculating one column against the remaining columns. And then formulate the error function. You need to define the error function just like what I did with j theta. But that error function need to include the rich regularization criterion. Then derive the gradient of the error of the in the second of the second task, right? Calculate the error, the gradient of the errors, take the derivative, and then implement the gradient descent, right? Using all data set, and then implement the stochastic gradient descent using subset of that set, and then repeat it for a number of iterations, and then test the effect of lambda. Try to see what would happen if you have a large value of lambda or a small value of lambda. Okay, and also test to see the sampling proportion in task number 5. Okay, the whole thing is actually just one task: writing logistic regression optimization with regularizations using stochastic gradient descent. But I break them down into 7 subtasks, so you can just follow it step by step here, and then prepare it as a PDF. And how to submit the work? You can submit the work to the LEB2, right, on before the due date. Right, I will put the submission slot into the system. All right, any questions? It can be about the assignment or about the lecture. No questions? Deadline is 14, yes. 3 weeks. Because we will have, as you have seen, you saw in the score distribution, we will have five assignments, and each one would worth about 10 score, I think, and the final exam is 20. And the exam, the presentation is 20, term project presentation is 20, and the exam that will be 30, right? What is the score of this assignment? 10, right? 5 assignment, 50%, so each would worth 10 score, right? Right, for the marking criteria, say if you do the work correctly, for this whole thing, right? Because as you can see, if you answer it correctly, then you get the score proportionately. But yeah, I will tell you again, maybe I will fix this file and then put in the proportion of the score in, so that it add up to 10, because this is 7, right? So you may wonder which one worth what, right? But you need to do it step by step anyway, because you cannot do stochastic gradient without doing the gradient descent. And you cannot do the gradient descent without having the derivative of the gradient function, and you cannot get the derivative of gradient function without formulate the error function first. Okay. Right. So I would distribute the score based on the complexity of the task. Like derivative would get more score for sure. Coding would get certain. Test would get a certain bit, right? But not that much comparing to the implementation. Okay, so I would update this and then post this onto the group within maybe tonight with a score distribution. And that would be good for anyone. Right? Any more questions? Okay. So what you have learned today is the concept of optimization using gradient descent. Optimization is a key technique in deep learning, because in order to make the system learn, you need to have a way to estimate the parameters that is suitable for the task. To let the system learn, you need to have a way to implement the learning process, right? And then for the deep learning itself, the system learns from errors. And you can see that today, these elements play roles in defining a way for the system to learn the parameters. And I hope that you have fun with the assignment. I find it quite insightful in when you take derivative here and then trying to figure out the way that to make the algorithm work here. All right. Any more questions? Explain. The term implement and the test in the context of the question. Slide 25 and 26. Does n represent the same thing? N. Oh, here. Oh, sorry. N. Yeah, I did not tell you before. N here indicate the number of points. I say if you have the data that looks like this, this will be n, right? And then the number of parameters would be like since we have xi here, then you cannot see. Sorry. How come? Oh yeah, I forgot to share. Okay, so n is the number of rows, and for each row, we have the number of parameters. Oh, I see what you asked. Sorry, this is a mistake. Right, this one should not be n. Say it's k. Shouldn't be n. Right. This is a mistake. Thank you for asking. This is k, the number of parameters, and this n is actually the number of points. This is k and n. All right. Yeah, because this is a summation of errors of all points, the loss function of all points. Why this indicate the combination, the linear combination of the sigma here. Oh yeah. And this is already correct. Where did I make it wrong? Only that, right? Only this. And yeah, this is correct. This is correct. Okay, so yeah, that's it. So here the summation here indicate the summation of the variables and the coefficient. So it should be certain numbers, right? Not n, and that means the number of point. Okay, good. That you asked. Right? Any more questions? Implement and test using code? Yes. Implementation here is coding. Test also means once you implement these algorithms, actually I would say just implementing the number 5, then you can test the parameter, you can test the effect of lambda. What would happen if you change the value of lambda? And then you can also test the effect of sampling proportion in the stochastic gradient descent. Okay. Yes, using coding. That means the part 1 is actually a coding task. Part 2, 3, 4, math task, mathematics, and then part 4, 5, 6, 7, coding. right? Okay. If you have more questions, and you can ask me later on. You can post in the groups, and that would be a good way because we can then update everyone that we can then update everyone in your questions, right? You can ask me in the private channel as well if you are not comfortable with posting into the groups. That's fine, right? If nothing else for today, have a good night, and yeah, you have 3 weeks for that. I will upload the assignment descriptions onto the group within tonight, right? So nothing else. See you next week. Next week we will take a look at the optimization. Like I said, the further algorithm in optimization and regularization. Okay. I think it is right. Next time is the but next time is more complicated. It's the basic concept of machine learning. Machine learning in math sense. You learn the concept of MLE and MAP. What that is. Okay. See you next time.